I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. And modern magnetic resonance for the molecular sciences is a course developed at ASU and uses the Magnetic Resonance Research Center for practically doing magnetic resonance. But a lot of what we'll do in the class is to look at the fundamental concepts and then be able to apply them practically. And information on the fundamentals of magnetic resonance and modern magnetic resonance will be put at biopchem.education, which is a website I maintain where I'll put all relevant links and information regarding magnetic resonance. So in looking at the fundamentals of nuclear magnetic resonance spectroscopy, it's really looking at the fundamentals of how nuclear spins interact. And this is one of my favorite kind of representations that generally covers the different types of nuclear spin interactions we can have. And what we'll be doing when we look at the fundamentals is really breaking down these individually. But what I want to do in this video is just quickly give an overview of some of the nuclear spin interactions. And these are covered in, great depth in books like, Spin Dynamics, which is the basics of nuclear magnetic resonance. That one and other books like, Understanding NMR Spectroscopy, etc. And I like to break it down this way because I think this kind of covers all of the basic concepts. So we'll cover in more detail later exactly what we mean by nuclear spin, but fundamental particles have intrinsic angular momentum. And so the nuclei of molecules can have, their individual nuclei, the sum of the protons and neutrons can have an overall net angular momentum associated with it, which will give it an overall, net magnetic moment associated with it. And it's really looking at how those can interact. And so the primary interaction is what I've drawn by this outer circle. So, and so the way we end up doing, whether it's NMR for nuclear magnetic resonance or MRI, magnetic resonance imaging, the first thing we do is take whatever we're interested in and we put it into a magnetic field. And so the interaction of these nuclear spins, the magnetic moments they create with this external field, in this case, we'll call it a static external magnetic field, is what I've drawn here as one and it's called a Zeeman interaction, but it's the interaction of these nuclear spins with an external main magnetic field. So this is why in MRI, this is why they put you inside of a large magnet. That's that external magnetic field. Or in NMR, it's why we take a sample and put it into a large static magnetic field, is for this initial interaction one here, which is the nuclear moments that are created from these nuclear spins and their interaction with an external magnetic field. So now you can have different nuclei, of course, and so they can interact with each other and they can do that directly. And we typically call these spin-spin type interactions or direct, nuclear spin interactions with other nuclear spins. And this can be either homonuclear, meaning different protons, for example, interacting with each other, or different carbon-13 nuclei interacting with each other, or they can be heteronuclear, like, for example, a hydrogen nuclei, a proton interacting with a carbon-13 nuclei. And they can do it in a very direct manner or through kind of dipolar direct magnetic spin interactions. They can also interact with the electrons in the system. So these are often molecules. They can have directly bound, so they can directly interact with the spin of the nuclei with electrons. So, And, this can cause the electrons can shield, the magnetic field, but they can also just directly interact with it here. So not only can the nuclear spins interact with electrons, and they can interact with each other through the electrons. So they can, in a sense, this spin can end up interacting with J either directly to here or because indirectly through 3. In other words, the nuclear spin here can interact with an electron and that electron directly interacts with J, because often electrons can be bonded. They can be bonded electrons or electrons that are shared between 2 different nuclear centers. Okay, so this can be either direct or indirect. Now, you can also interact these nuclear spins with phonons in a system, and we typically call that the lattice. So directly looking at phonons, acoustic or optical phonons in a system, or in a sense, what we think of molecularly as the vibrations or the sound waves, right? The acoustic sound velocity or density fluctuations through a system, etc. And this is often one of the things we look at, especially when we look at relaxation, of how these nuclear spins can end up relaxing if you've tipped them away from an equilibrium. So, and then like we said before, just like you can have indirect spin-spin interactions, you can have indirect spin-lattice interactions through the electrons. So you can have these nuclear spins interact with the electrons up to 3, and then those electrons interact with the phonons of the system, the lattice of the system. So you can have this indirect spin-lattice interaction. So, and then another one, which is very important in chemistry, especially in looking at molecular configurations, is the interaction of these spins with the electron, and then those electron, with the external field. So some type of shielding, what gives us the chemical shielding properties. So while the indirect interaction through electrons can give us something like the J coupling, it can also give us shielding because of those electrons. And one of the things that gets used very recently a lot, like something like dynamic nuclear polarization, is you can also use this as a polarizing effect for the nuclear spins as well. And then finally, you can have these interactions with the phonons and those phonons with the external field, or kind of some type of sound field. This gets used a lot less commonly than, for example, the shielding one, but it kind of completes the overall different types of interactions. And then the external field, you can have the main static field, but we often, have oscillatory fields as well. And so the way we're going to, approach this from a fundamental standpoint is to look at this by its energies. And in quantum mechanics, those energies come through the Hamiltonian operators. And so we're going to be looking at the Hamiltonian, and we can split this up between the external Hamiltonians, in other words, the interaction with the external fields, whether it be the a B0 static field or B1 oscillatory fields that we use for rotating or excitation of the spins, and then all of the different internal Hamiltonians associated with it as well. So for example, what we said, like we can have spin type Hamiltonian interactions, direct dipolar, etc., of 2 different spins. You can have heteronuclear spin interactions. You can have spins when that have internal degrees of freedom because of they're greater than spin 1/2. So quadrupole type interactions, where it's not just a dipole, a spin 1/2, where there's kind of 2 poles associated with, but there's multiple poles within a single nuclei. We can have, again, these chemical shielding type, this 3,6 type chemical shielding, and we can have this, down to 4 or 4,7, like the lattice type interactions. And we can express each of those, we can isolate each of those internal Hamiltonians and look at their interactions explicitly. And that's often what we'll do when we start looking at some of the fundamentals of NMR. So hopefully this overall kind of pictorial diagram gives you a general sense of, in a sense, some of the fundamentals of nuclear spin interactions and how many different types of interactions, both direct and indirect, are possible, and why, you know, it's one of the fundamental reasons why nuclear magnetic resonance is so rich in being able to give us molecular level details, because of its interactions with electrons directly, indirectly, with lattices in a system directly and indirectly, and how all of those can couple to a field. Thanks.